So it will be the last 30 minutes, 20 minutes about statistics. And after we forgot a little bit some statistics and we go more in deep learning and machine learning. So just I wanted to be clear that when you do a linear model in these figures, we have two features, x1, x2, and we have an outcome y. And what is doing a linear model is looking for a hyperplane. So we are in 2 dimensions because we have two features. So we try to find a plane which is going closest to your data set. Something linear, so an hyperplane. But when you do a logistic regression, something nonlinear, and you can see that is not an hyperplane. So what is the difference between the logistic and the linear regression? But if you use when you have a binary outcome, so it's more natural to use a linear model. And did you manage to get this around on this example? So on this example is from data which is quite well known and is available. So you can Google and you will get the data easily on breast cancer study. And we try to discriminate some benign, which is our outcome is 0, and from malignant, which outcome is equal to 1, from lumps of a breast mass. So we have put just pictures, and from this image, they collect 30 characteristics. So it's 30 features from each patient. Make sense? Let me know if you have something trouble with the data. And I just run a logistic model, and after to see that is also we can see this like a shallow neural network. So I just go very quickly on this. And I'm going to slide 30. Okay, so just to explain what is going on. And so if I just have one features in this data set, I just use the feature which is the mean area of the mass. So for on the X, you can see on the X here. So I just one features, and I have some outcomes. So the outcome is benign, so 0 or some 1. And I try to fit a model. So what I are looking for when I want to see if this feature can be a good predictor or discriminate my two population, I try with a linear logistic model to, in fact, predict the probability of my outcome is equal to 1 for malignant, given some features. And here I just one features, given X. So this is, I try to build this model. So I can do a linear model with the red line, but we know that it's not good. And I can ask why it's not good. So why a linear model is not good on this, to do this model? I have asked a question. Yes, the output is not a probability, and you can see on the line, very good, that the prediction could be negative, so it's not a probability, and could be greater than 1, okay? And so I run this model with this simple model with this variable, and I got this. So how is called this kind of table? What is the meaning of this table? I just asked some question to see if you have read the lectures. Okay. Yes, we want an output between 0 and 1. So is the reason why we do the activation function, the sigmoid, because the sigmoid is going from R to 0, 1 interval. So let me know about this table. What is this table? Okay, I can put a table if you want. It's not really a nice table, but now it's a table. Confusion matrix, yes, is a confusion matrix. Okay, so this is, the reference is the true, and this is a prediction. Okay. So, for example, just to remind what we have done with 138, what is this in the coefficient matrix? We need to choose between TP. Ah, yes, TP. Okay, everybody is happy for TP. So this is TP. Okay, true positive. We detect malignant cancer, and it was malignant. Okay, this one. Yes, true negative. Very good. Okay, this one, the 37. So we didn't detect, we say no. And in fact, we have to say false positive. Yes. And of course, the last one is the false negative. Perfect. And from this coefficient table, I managed to get an accuracy of this one. So, okay. And in my sample, I have asked a question, which is quite straightforward, but I wanted to know if you get the question. I'll just go through the question I put on the slides. So I have 401 correct prediction, 55 incorrect. So it gave me this like an accuracy. But I have used just 456 samples and not 569. Why? Okay, question of Matthew. You need to reply to Matthew first. Okay. Very good, Richard. Very good, Anne. Anne is back. Okay. But we need to reply to Matthew because Matthew have a question. If we predict 1 positive malignant and it's actually 0 benign, is it a false positive? Yes. And we have didn't say this. Predict. Oh no, it's here. False positive. False positive. Yes, right. Oh, very good. So this is a false positive. Everybody is agree? Okay. Thanks, Matthew. So yes, in fact, I haven't see this, but I remove some data just to see if to do some training set and the test set. So just do not overfit my data, okay? So I want to know, in fact, I need to build a classifier which will be good for a new patient, okay? So I need, in fact, to evaluate my model on the test set. Okay, good question. And the way to do this is called to generalize. So we want to know how our model works on new data we haven't seen for the training part. And there are different options to do this. So we'll talk about this later, but just to say you have the first version is all out cross validation. So training set and a validation set. Or you can do also some k-fault cross validation. And we will see later that in fact, the best strategy if when you have a lot of data is to cut your data in three sets. Okay? Training, validation, and the testing when you do deep learning. So after I did, I will use more features to have a better model. So the good way I do 2 predictors. So everybody is comfortable with this plot. So I put my 2 predictors. I have these features and these features for each breast mass, and I have the red and the blue, which is my output. And I want to classify, in fact, to discriminate this benign and to malignant. So I did the logistic model, and just to know that this is my output. But maybe when you see this, so this have been done from my model, logistic model, or my sigmoid model. And you can see that before I explained that the logistic model, the sigmoid, is something non-linear, is non-linear function. But when we see this result, it may be something, maybe trouble, because you say, oh, I did something non-linear, but my boundary decision is linear. You can see that this is after this line, below is predict red, and above is predicted blue. So why is a linear decision boundary? This is my question. Because we use something non-linear, an activation function, but my decision is linear. Do you think is this weird or is pretty obvious? Or do you need some explanation why is linear this boundary decision? No communication, please. Yes, please. Ah, okay, Jade. Because you ask, please, I will give you some details. Okay. The level curve is of nonlinear function. Yes, it is because it's only the center of graph. Okay. Okay, I will do a little bit some explanation. So the logistic model, I will not explain the logistic model. You have the slide, you have read this, but he gave us, we try, the output is the probability. We estimate this. And in my example, theta is my parameter and x is my features, okay? So at the end, my model gives me this, the probability to be equal to 1, my outcome is 1, given some features. So n is given by this function, okay? So now when I want to classify, I need to do a cutoff. When I got my confusion matrix, I did a cutoff. And the natural cutoff is if my probability is greater than 0.5, my fitted model, my prediction is greater than 0.5, I will say 1. And is lower than 0.5, I will say 0. Make sense? Okay, so I'm doing this. I try to find some place to write something. Yes, I would write here, maybe. So what I've done is the probability of y equal 1 given some features is given by my sigmoid, which is 1 divided by 1 plus exponential minus, I put a theta, so theta transpose x. Okay? So now I need to do my decision rules. My decision rules I will compare to 0.5. So if it's greater than 0.5, I will say 1. And otherwise, I will predict 0. Make sense? So what is my decision, my boundary, if it's linear or not? So 1 is greater than 0.5 is when 1 plus 1 exponential x is lower than 2. So is the meaning that makes sense? Exponential minus x is pretty by 1. When is this greater than 1 is when the x minus 0 transpose x is lower than 0. Make sense? So this is my decision. So is when this linear predictor is greater than 0. And this, what is this? Is just an equation of a line, because this is theta 1 x1 plus theta 2 x2 in my is greater than 0. So this is an equation of line. So in my plot, it was just a line given by this estimation. Make sense? Clear? Not clear? Yes. Okay. So keep in mind that, okay, it could be useful, but if you have something which is not separable by a line or an hyperplane, it will be not good. And so the good way to improve, to have something nonlinear with the neural network is to add some layer. If you add one layer, you will get something, a decision which will be not linear. Yes, in this case, Matthew is right. The decision process is linear because we didn't have any hidden layer. But when you will do I think you will do this during the assignment, you add one hidden layer and you will have something non-linear. And I will do it in a practice to show you this. Okay? I hope you get something today. So I'll keep going. So in same way as the linear model, the logistic model can be viewed as a shallow neural network. And this is, you have your features there. This is a nice picture, I like this. So the sum symbol will give you the linear combination of each features with some weight. And after you applied an activation function, which is here a nonlinear, which is a sigmoid for the logistic, and you got an output, but the output, be careful, the output is a probability. Okay? And now if you want to decide, you need to decide with a cutoff. Yep. So this is our logistic model. So the statistician doesn't see the logistic model like this, but it could be exactly similar, exactly the same. Okay. So I say, and which figures I like is these figures, just to really understand. And now I will not use, not too much, the notation theta, which is more using in the field on statistics, but in deep learning, we adopt the notation W, which is a weight. Okay, so you have your unit. The first part in the neuron is you doing this linear part, so the linear combination of the weight with the features. You add a bias, and from them you do this is called annotated Z, and you apply the activation of Z, and you got this value, which is just a real value, and in a simple shallow neural network, it gives you the output. Okay, so the output of a neuron will be later the input for a new neuron. If you think that, I know that this, I'm very bad with this. I need to find where again. Yes, yeah. You can think that maybe this neuron will connect with another neuron. Okay, later. So the output will be the input from another layer. Okay. Okay, so I've noted after we are with the slide 38, I say I want to talk about the 39. Yes. So the quartz entropy. So keep in mind that for binary outcome, we use the quartz entropy. And we will see today that we use this quartz entropy because it's handy, because it's a convex, it will give us a convex optimization problem. And just to give you intuition that the quartz entropy is a good way to evaluate if our prediction is close to our real value. So if we observe an outcome which is equal to 1, and if, for example, our prediction is something close to 1, the log of 1 give us 0, so lower loss. So it's quite okay. But if the position is close to 0, the log of 0 is minus infinity, minus infinity is plus infinity. So if our position is 0 and the current value is 1, our minus log of the position is pretty bad. So it gives us, for this part, the design of a log function. Okay, now, and if I'm going to 0, if I observe 0, and I predict which my position is close to 0. So if my position is close to 0, 1 minus my position will be still close to 0, and the log of 0 is also minus infinity. And I did a mistake? No, okay. Oh my god. Sorry. It will be close to 1, and log of 1 is equal to 0. So is the meaning by my loss is very low. So which I want, because my position is very low. Okay, it's just to give you the intuition of the cross entropy, which has the desire of for a loss function. Clear? Okay, I keep going. If it's clear for the cross entropy. Okay, and after I say, okay, I want to come back to the 44. I think in my previous slide, I put some, there's some error, but I put correct on this slide. 44, 44, 44. And after I will reply to your question of this set of slides if you have any question. Okay, okay. For the multi-class classification is the meaning that we want to do some classification when our output are more than two values. So we have a prediction of a discrete value, but greater than 2. So for example, you have work with the NIST data, this one, which is, if we want, in fact, is not, don't want to predict a real value, we want to predict if it's a class of 0, a class of 1, and so on, and so on, and so on. So this is an example which is works. And you have also another example which is works. What I put, classify email. So, for example, I have some email. I want to classify directly if it's a spam, is it an email from a traveler, if it's an email from work, or is it a personal email. So in my cases here, my outcome k is equal to 4 classes. Okay, so for doing a multi-class classification, which activation we use? Which activation we use? Softmax, thanks. I used to give some award for the people who are the faster, and I give some chocolate, but virtual chocolate is not so good, huh? Okay, so just keep in mind, because we will use later for this one hot vector calling and one, or it is called also one of k encoding. So you have your outcome, which is a class, discrete set, which is 1 until k, but we need this in practical in our algorithm to do the optimization problem, to code in with this one hot vector, which give me a 1 for the entry k. Okay? So keep in mind this. And now the softmax is related to the multinomial distribution, but the good point is these nice pictures I want to show you. And this nice picture at the beginning, if the people have seen the slides, the draft before, I did this by hand, and thanks to Sarat, we have these nice pictures. He did this in, I don't know in what, but So is to understand the softmax model. So you have your input. So this is called the input layer. This one. And this, in fact, this first neuron. So the choice of the number of units here is given by the application because we have k classes to discriminate. So we have k neurons, and all this arrow from which going from to the first neuron give the first part the linear part with a specific bias and an activation. And this we will give the probability to be in a class 1. For the second neuron, it gives us the probability to be in a class 2. But all of these are connected. They are not completely independent. And you can see the dependence is there. I just come back slowly because the probability of each activation part is given by this. On the numerator, you have the exponential of the linear part, so the first neuron. But on the denominator, to normalize the probability that the sum of each probability need to be equal to 1, we divide by the sum of each of the neuron. So it's a meaning that is not the neuron are not independent. This probability. So it's not like you separate your model and you calculate k logistic model. It's all together. So at the end of your neural network, it gives us, in fact, a vector of probability. And how to decide which class is this, you will take the maximum of the probability. So K hat, I will say, is the arg max of the A K, which K is going to 1 to K. Make sense? Okay, on slide 45, what is mean by we set theta k equal 0? Yes. So is the meaning that, in fact, in practice, it's just technical, is because that you have the sum of the A, I will say A k equal to 1 to k equal to 1, is meaning that they are linked. So instead it's just to parameterize your model, because one parameter the last one set of parameter can be deduced from all the other due to this this dependency, this equation. It makes sense? So it's a meaning that if we know theta 1, theta 2, theta 1 and so on, you can get the, so it's just yes, okay, thanks. Oh my god, my explication was so bad. You got it, but it's recording. Everybody will see my bad explanation. Okay, cross entropy. We use the cross entropy also for softmax, but it's a cross entropy for categorical response. So the cross entropy is given there. So it's kind of similar as the cross entropy for the binary. But be careful, I have this notation which is important, is ND. This is a binary variable which indicate for the cross entropy, be careful, which indicate is 1 if in the class binary, yes, the definition there. Okay. So it's also a cross entropy, but for the categorical variable. That is for this part. Do you have any question before I'm going to the second set of slides? What are metrics? Okay, question. We all together we reply to metrics. The metrics are to evaluate the performance of your model. It's a very good question. Thanks to ask this question, because which slide it was? I don't remember. Metrics. The slides where I define metrics. I think I define the metrics here. Yeah, it's good point. Metrics. So the metrics, the different metrics are when you do some classification, you can compute the accuracy, but you can also compute the precision, the record, and the F1. So it's the main metrics to evaluate the performance of your model. And all of these metrics are computing based on the confusion matrix. I don't know how you put the confusion matrix. Is okay? Yes, I see, thank you. Okay, so I didn't put the formula here in purpose that you do your job to write exactly now when you have the precision or recall F1 to know how to compute this based on the confusion matrix. Okay? So put a small note and you know how to compute this. And also, I don't have too many times, but another way to evaluate the performance of your model to know if it discriminates well in a binary classification is to use which we call the area under the ROC curve. And the area under the ROC curve also computed thanks to the confusion matrix for different cutoff. And this is also given mainly after your model, the AUC, and you want to have the AUC the closest to 1 as possible. And just to keep in mind that if you have the AUC around 0.5, is the meaning that you are not better than to draw a coins to decide if you go into 0 or 1. Okay? Okay, blah, blah, blah. I'm going to the second slide. Tuck. I'll let you all to take the second set of slides. You got this? So today we will talk, it's like a warm-up for your series of lecture on optimization. Okay? Just a warm-up for tomorrow. So I will talk about convexity, and we see the linear case and the logistic case, and we'll talk and optimization with the gradient descent and some regularization. Okay? You have the slide. We're ready. I don't see the face. In fact, I don't know how to put to see the face. I don't know. I don't know the video. I don't know. Okay. Okay. I keep going. Nobody tell me. Somebody. Okay. Convexity. First question. Up. Convex. And I don't accept a response by a chat. I want to hear some voice. Most of you know this. Some people are doing the unapplied math. So what is the convex set? A set C is convex if any point in C. And if you take the value of theta between 0 and 1, and you compute theta x plus 1 minus theta y is in the set. So by definition, if A and B, I have two sets, which set is convex? So the idea, you take any point in your set and you draw a line, and all the elements from the line should be in the set. The good response is A, but now you can consider I'm blind and I just hear some people. I want to hear some people.
Hi.
Thanks. Good. I got it. I'm happy. I'm not by myself. Okay. So it's pretty clear. Convex function now. Definition of the convex function. So I put the formal definition here. And if you're looking at this formal definition of a convex set, if you have a function, well, I take just a function in R. So you pick any point of the graph of your convex function, you draw a line, and the portion of the function between these 2 points will lie below the straight line. So in my example, this is a convex function. Make sense?
Yep.
This is a convex function?
No.
No? No. Why? If I take 2 points, it's okay?
If you take a point either side of the middle rise.
Yes. Thanks. Okay. Okay, so you got it, the convex function. So how to show that a function is convex? I put two conditions, which you can use any of the 2 conditions to verify. So it's called the first order condition. So if you take, if your function f is convex, if only if you have this inequality, and I'll let you just relax to look at this inequality and to think about how I can represent this inequality. And I put some note to explain what is this, represent this equality. So if what your function f is convex, you take the tangent line at any place and is a global estimator of your function, underestimator of your function. So it's the meaning that at every point the line, if you take the tangent, my function will be, the point of the function will be above. So I put here, but if I take here, it'll be the same. If I take a tangent here, it's the same, and so on. Okay?
Shouldn't the inequality be the other way around?
Oh. Fy. Yes, you're right. Good point. Y minus 6. Yes, because my line is there, and this is also right. Good. Thanks. Who did this? Who said this? Okay. Okay, thanks a lot. I can say on the video, it was in purpose to see if some people follow. This is a pedagogic tool. Thanks. Second order condition. Check if I did something wrong. Second order condition. Assume that you have a function from Rn to R and is twice differentiable. Then your function is convex. If your domain is a convex set, the domain of your function is a convex set, and the Hessian is positive semi-definitive. Semi-definite. Okay? So the notation is this for Hessian positive. So the Hessian is just the second derivative of your function. And if you do the second derivative, you compute the Hessian and is semi-definitive positive. So you show that your function is convex. Okay? And I just put this reminder in math, but for any symmetric matrix, M is positive semi-definite if we have X transpose MX greater or equal to 0 for all X in Rn. Okay? Okay, maybe you will have an exercise soon. Example. Okay, I will just pick up one or two very quickly. I put some example of function which are convex. The function exponential, is it a convex and why?
When you take the second derivative, is positive.
Yes, thanks. You take the second derivative, is positive, convex. A negative logarithm.
Not for the real numbers, just for the positive numbers.
To put this, sorry?
Just for the positive numbers, I was going to say.
Yes, yeah. Yes, you take the second derivative, it will be also positive. Okay. So the affine function, a linear, of course, something linear, it will be also convex because you can take the tangent and it works. I will let you to do this proof, which is quite nice. So for any norm, by using the triangle inequality, you can show that the norms are a convex function. And we will not prove this, but this is quite handy also. If you have a linear combination of a non-negative weighted sum of convex function, it will be still convex. So each fi convex function, I take a linear combination with some non-negative weight, and it will be convex. Okay. Okay, why convex is important? Convex is important because for your convex function, your critical points are minima. So we guarantee that you got your global minima. Okay? And so if you know that you have a convex function, you'll be sure that if you're using a gradient descent, you will find it will work. But with no convex function, you can be like something like a gradient descent could be just stuck here. Make sense? Okay. On convexity, composition of convex, this is important. Convexity, the composition of convex function is also a convex function, and the maximum of convex function is also a convex function. So keep in mind this, and you will have a work. So I put this here as a road map to prove convexity. So try to, by definition of convexity, or computing the Hessian of the matrix, you'll maybe decompose your function of non-negative weighted function of sum of convex function, or is a composition of an affine convex function with an affine function. And the last one is the maximum convex function. So by doing this, I can tell you that when you do the shallow neural network with the linear model, and if we use the least square loss, is convex. So your optimization progress is convex. Why? Is because this square loss is a convex function in respect to if is a function, if you see the least square as a function of y hat, this is a convex function. Make sense? The least square for this function is if I say f y hat is equal to 1, check, I say this is a convex function. Okay, I don't know why is somebody say merde. What's the problem, Stefan?
So this function is not convex as a function of y, right?
This function is not convex as a function of y. Why you say this?
Because you say it's convex as a function of y hat, but not y.
Ah, yes, it's also convex as a function of y. I still don't get Stefan. Okay, y? Yes, it also convex as y, but my point it was I wanted to see if it's convex of y hat, because our weight when we do the not optimization problem, I remember that y hat is in fact is given by wx plus b. Okay, so when I do my optimization problem, I want to get is my cost function, in fact, is g of w, which will be the sum of y equal 1 to n to 1 over 2, I put here, if you want, yi minus y hat I square. Make sense? And I want, in fact, to have my optimization problem in respect to w. So I just wanted to put something in comparison to y hat and do the composition of function.
Yeah, it
Is
makes
it more clear?
sense.
Yeah,
Thank you.
makes sense. Okay. So now I say, okay, this part is convex as a function of y hat. Is also convex as a function of y. This makes sense. Okay, but it was not my point here, but it's true. You're right. This z part is also a linear function of w and b. Okay, is a linear function of w and b. And we have seen just before with like property that now we do the composition of a convex function with something linear, and we say that this we know that is a convex function. Okay. Yep, so to show that our optimization problem for the linear model is convex. Okay, now, of course, we say we want a break, and nobody told me to do a break. Christina, we reply to Christina, and after we do a short break. And this is your homework. When I do I put some homework and I don't have time to do the work in progress and to see if you get it. You try to do by yourself, and if somebody send me an answer, I'm happy to put the answer and to give to everyone. So you need to do the work, okay? No, it's an assignment question. Very good. I will not do it. I remember I did. Okay, we reply first to Christina. Christina asked, my function, why this one is still convex if y hat is negative? Is a function. Huh? Okay, so how to prove that this function is convex? If somebody can help Christina. This is a function of y hat, okay? I can plot this function. Take the second derivative. Yes, take the second derivative. What is the second derivative of this? One. Thanks. So it's positive. No, Christina, Christina, we do step by step. The first derivative is minus y hat. Yep. And so, and after this is equal to minus 1 plus y hat, and I take again the derivative is 1. Is no silly mistake. It's good to do a mistake. Okay, good. Break. 5 minutes break. What do we say? Push up or we take a coffee? Okay, I will take a coffee. Nobody told me to do some push up. Coffee. Thanks. Well, okay, I stop the video and I come back in 5 minutes, okay? And we start again at 4.